Okay, so we're reviewing some probability before you get to your IB exam. So this is stuff that you learned back in Math 20, but I'm pretty sure you did it near the end of the course. And probably, I don't know if you had a test on it, so it's a good idea to review. Just going to minimize it a little bit here. Okay, so basically you have to just set up an experiment with the results already given, and then we're going to do some verifying. So this is rolling a red die and a blue die, and the outcomes are given there in this table of the total of their sides when they're rolled. So event A is the sum of the two dice is 10, so that would be these three results, and event B is the sum. The number on each die is the same. So when you roll 2 1s, you get a 2, 2 2s, you get a 4. So that would be these. Okay, so probability of the sum of the two dice is 10. That's 3 out of 36, which reduces to 1 over 12. Sum of the dice is the same. That's 6 out of 36, which reduces to 1/6. And the union. So where do you get all of those events combined? You don't want to overlap anything. So there's 1, 2, 3, 4, 5, 6, 7, 8. We don't want to count the 10, that middle 10 twice. So there's 8 out of 36, which reduces to 2/9. Then we get into conditional probability or dependent. So that's the probability of dependent events. So this is probability of B, given that A occurred. So I always think about this as now, with this, I've reduced my sample space down to just A. Okay, so what is A? The sum of two dice is 10. So I'm just going to erase this. So the sum of two dice is 10. I want to know the probability of B, that's the number on each dice is the same, given that the sum is 10. So that's only 1 out of 3. Okay, so it's reduced that sample set. Then vice versa, probability of A given B, so B is the number is the same, that's all of those. And probability A is the sum of the two dice is 10. Well, there's just 1. So 1 out of 6. Okay, so basically this is your new sample set. Okay, intersection. Well, where do they intersect? That's that 10 right there. Okay, so that's 1 out of all of them, 36. Order of showing the intersection doesn't matter, right? These are the same. So just realize that. So then more specifically, dependent events, as I talked about, those events those are events whose outcomes are affected by each other. For example, if two cards are drawn from a deck without replacement, the outcomes of the second card depends on the outcomes of the first, because you're down one card first of all, and then what was it? Do you still have a heart available or a 10 or whatever it is? So here are dependent events. We talked about, so the probability back here of rolling 2 the same, given that the sum was 10, that depends. You had to know that which events had a sum of 10. So those are dependent events. And then based on the dependent events, we can calculate probability. So really these are kind of the same. It's just these are actual events. So you could look at the number of items or the probability. Now we're just talking about probability. So that's the probability of an event occurring given that another event has already occurred. So the second depends on the first. Okay. Here is the formula. It's in your data booklet. So this is the probability of B happening given that A already did. And so that's the intersection of the two events divided by the probability of A. So I always remember these are matched up. Back in a number of years ago, we used to teach pure 30, not 30-1. It's called something else. And they included probability. So they would have this version of it on their formula sheet. as opposed to the division version. It's just rearranged, right? So again, these match up. But this is what's on your data booklet, okay? So we're going to verify given our example above. So I'm going to do it left side, right side. So intersection is 1 over 36. Probability of A was 1/12. Okay, and probability of B given A was 1/3. Which is 1 over 36, left side equals right side. Okay, then we'll do this one. Okay, so left side and right side. So this is just with regards to event A occurring given that B already did. So it's the vice versa, basically. And then probability of B was 1/6, and A given B was 1/6. Okay, so that just verified it. Bayes' theorem is given there. Really, take a look. This is B given A, this is A given B. So it's a way of finding the sort of the opposite conditional probability. And so we'll verify this. So B given A, sorry, I can't remember all of these. B given A is 1/3, A given B is 1/6. And probability of B was 1/6, 12, 6, and then probability of A is 1/12. Okay, so I'm running out of space here, but that's 1 over 36 divided by 1/12. Invert and multiply, so that's 12 over 36, which is 1/3. Okay, so sometimes that's an easier way of finding the other probability, conditional. We will, in the next lesson, so tomorrow's lesson, look at the formula that is listed for Bayes' theorem in your data booklet. It's a little more intricate because it involves a sum of probabilities for this, okay? And so it's still Bayes' theorem, and actually in today's lesson, we're actually using Bayes' theorem, whether you know it or not, later on. I tend not to sort of think about the formula. I try to think through what probabilities I need. So in any case, it's there if you need it. We've just verified it. Then we get into mutually exclusive events. So again, review from back from Math 20. You kind of did a lot of this stuff, mutually exclusive and non-mutually exclusive, with your Venn diagrams. But it works with probability. We did a little bit with probability in Math 20. Yeah, so these formulas are in your data booklet. Basically, it's saying if you have mutually exclusive events, then if you're finding the probability of the union, so the total of all of those events, you just add the probabilities together. If they're non-mutually exclusive, that means there's an overlap, okay? It means some parts of A are also in B and vice versa. So the union, if you add these together, you are adding the overlap twice. So you want to subtract the overlap, the intersection, okay? So again, it's not very, the example that we started with, those were not mutually exclusive because there was that 110 that was in both sets. So the union of all of that, remember the left side, the union was reduced, was 2 over 9. If we look at the right side, probability of A was 1/12, B was 1/6. And the intersection was 136. So now if we get a common denominator, that's going to be 3 over 36 plus 6 over 36 minus 1 over 36, which is 8 over 36, which it reduces to 2/9. Okay, so that just verifies it. So here's an example like we did in Math 20. So Ms. Cheney surveyed her students that had fitness room memberships to see if they do cardio training or weight training each week. Assume that they all train each week. So some obviously would do both. We're told here that students do cardio training, 0.74, so this whole circle is 0.74, and then this would be weight training. The whole circle is 0.42, but the total is 1, right? We'll do that in red, right? Total probability, because they all do at least something in the week. So, and if you add these up, you get more than 1. So there's this overlap here, okay? So in terms of the formula, so here we can call it C and W. So probability of C union W is the probability of C plus the probability of W minus the probability of C intersect W. Okay, and we want to do both. So we want to solve for this. So if I bring that to the left, that's C intersect W. So basically you're adding up the individual sets, the probability, and subtracting the union of them. And that will give you what the overlap was. So in this case, cardio was 0.74, weight training 0.42, minus 1, so the whole thing. And that's 1.16 minus 1 is 0.16. So that is this part here. We filled in the rest. That would be 6, 8, 0.58, 4.2, so that would be 3, 6, 0.26. And then if you add this, oh, not that. If you add this and this and this, you should get 1. Okay. Here's a pretty straightforward one. I don't even think about a formula really for this. Sammy draws 2 cards from a deck of 52 without replacing the first. Calculate the probability that Sammy draws both hearts. So think about the first heart. There's 13 hearts out of 52 cards. You've drawn it, so now, and you're not replacing it. So now you're out of 51 cards, and you drew a heart. So now you're down to 12. So if we simplify that, that goes into 4 times, that goes into 3, 3 goes into this, 17 times, okay? So what is that probability? So this is, so really we did probability of the first heart times the probability of the second heart given that the first was a heart, and that's the probability of H1 intersect H2. Okay, so this is probability of H1 intersect H2. Okay, next one, sometimes tree diagrams are helpful. Okay, so it says here an urn contains 5 marbles and 2 green marbles. 2 marbles are drawn, determine the probability that the second marble is red. So here, in your first choosing of a marble, you have a red or a green. And so the probability of getting a red would be 5/7. Getting a green would be 2/7. And then for the next marble, depends on what you chose first. Okay, so if we get a red here, we already had a red taken out, so that you'd only have 4 left out of 6 marbles. Green, you would still have 2, but out of 6 marbles. Then red and green here. So you didn't choose a red, so you'd still have 5 available, but out of 6. And green, you chose 1 already, so now you have only 1 out of 6. I'm not going to reduce them because we might need a common denominator. So here, determine the probability that the second marble is red. Well, that's this and this. 2 places. Okay, so this is going to equal 5/7 times 4/6 plus 2/7 times 5/6. And that's why it's easier not to have a common denominator, not to reduce it, because now we have a common denominator of 42. So 20 plus 10 is 30 over 42, which is 6 goes into that 5/7. Okay. So that's where a tree diagram is really helpful, right? And within these are each dependent probabilities, right? Because you're not replacing the marbles. And then the last one for today says each day a teacher gives the class a warm-up question. It's a numeric response question, 40%, multiple choice 60. Then Bobby gets 80% of multiple choice correct, 70% of the numeric response correct. Bobby answers today's question correctly. What is the probability that it was a multiple choice question? So probability of multiple choice given it's correct. So let's just set this up. First of all, we have to have the questions. So numeric response and multiple choice. So numeric response, 40%. I'm going to use the decimal form of the percent. And then that has to be 60%. Then if he gets it correct, if it's a numeric response, he gets 70% of them correct, 0.7. So he will get then 30% incorrect. You could also use a C prime here. Prime, so C and C prime, this would be incorrect. It's a complement of the original. It's the opposite. Then for multiple choice, he gets 80% correct, and that means 20% incorrect. So we want to find the probability of multiple choice given that it's correct. Well, that's going to be probability of multiple choice intersect correct, divided by probability of being correct. Okay, so multiple choice and correct is this. So that's 0.6 times 0.8. Then just the probability of correct, well, he could have got a numeric response correct as well. So that's then this and this. Total probability. So that's going to be 0.6 times 0.8 plus 0.4 times 0.7. Okay, so 0.48 plus 0.28 is 0.48 over 0.76. Do that in your calculator. And you get, I kind of did it already here. Oops, 0.48 divided by 0.76. Yeah. And IB wants 3 decimal places, or 3 digits. 632. Okay, so that's it for that lesson.